Okay, I believe we are live, which is good, finally. This was supposed to be streamed on the 9th of November from home, but my Wi-Fi could not handle doing a whole live streaming setup. So I'm trying it again, this time in the office, and hopefully we'll have all the bandwidth that we need to do all of this. So let's start off very quickly. If you're joining this stream and you don't know the context, I made a 4-minute video earlier this week describing what I want to do. I want to build a project in C++ that does all sorts of video processing to create an app that can be used for live performances, to create visuals for live performances. And I thought it would be very interesting to live stream the entire development process to kind of make this whole field a bit more accessible, because from my experience of just exploring these libraries and trying to learn how to do this, how to code this project, I found it quite tough to get good resources on how to do things. I was stuck for like 2 days just trying to get the library to link properly and to compile. So I want to go through, and as I solve these weird problems, show them to you, and hopefully if people join the stream they can aid me as well. So if I'm struggling with something, maybe you can spot it and help me out too. Okay, so overview of this stream. I'm going to first explain in detail the app I want to develop. If you're not interested in that and just want to learn how to set up FFmpeg and how to start decoding video files in C++, skip through to a specific point in this video where I start doing that. I'll put that in the description. If you're watching live, obviously you will have to listen through the first explanation. But yeah, first, I'm going to explain in detail the app I'm going to make. Second, I'm going to set up a basic app that allows us to display things on the screen. I'm going to be using OpenGL for this, and that's going to help in what we're going to do later, which is decoding video files in FFmpeg. But if we have a basic app that can display stuff on the screen, then we can start displaying the stuff we're decoding on the screen. So I want to do both of those in this one session. Right, so what is this app that I want to make? If you've seen the video, you've already heard about it, but I will give some more context this time around. Essentially, it is a visualization tool that should embellish a live looped performance for music. And I'll give you the example that I used in the initial announcement video, and we can look through that for a second. So this is me in my bedroom at like 1 in the morning recording a live looped performance. And how that all worked is I set up, let me show you the Ableton project if I can find that real quick. Stream announcement? No, stream demo, streaming. Demo song live project. Okay, so what I wanted to do is create a couple different layers of harmonies that I would layer up and then could play in the chorus. And the way I did that in Ableton is I've got everything in the arrangement view. When I start playing from here, let me set up the right, that should be correct. So we've got this sample that I'm using from Yusuf Day's Alpha Mist, Love is the Message. And it starts with all of this. Not sure if you can hear that. Yeah. So we start with this loop here. And here I start recording, like the automation allows me to start recording a looped region of a bass. And then we play this guitar loop and I start recording with automation a vocal, followed by another vocal, followed by another vocal. So the time at which I record all of my loops is set ahead of time. So it will look like this in the end. So that's my bass loop, and that's looping now. And here I'm laying on another harmony. So we've got two of them at the same time now. If I skip through the video, we'll get multiple layers. We have like 3 layers. Now we have the verse. The audio quality here is shit for some reason. And now we get to the chorus, and we have those backing vocals again. So, I don't want to go into too much detail here, but during this performance, I was recording loops, and later on in the performance, I'm playing those loops. And I can explain that to you now because I'm sitting here like separate from the performance. But to anyone in the audience that's not completely paying attention, when they hear this chorus, it might sound to them like I'm just singing one thing and playing one thing, and everything else is just a backing track that's been prepared. And they might not be quite as engaged in the performance because it appears to be just a performer doing one thing. It's not a very impressive feat. However, looping all of this stuff and recording everything in the moment live, that is actually quite impressive, and I think that is quite an interesting thing. I want to draw attention to the fact that this is all looped live, and I want to show that on a screen. I want to project something so that people can see, so that they can see what they're listening to. And the way I suggested doing that in my stream announcement, if I go ahead here, was like this. Hello, my let me find it. Yeah, this is how I wanted to loop vocals. Perhaps they would look a bit like this. When I take the picture. So during the chorus, you would see a video for every sample that's being played. The only thing missing here is the guitar sample because I don't have a video for it. But you would have videos of pre-recorded samples, and you would also have captured moments from the live performance being projected on the screen. So I want to have a live looping app that follows exactly what's happening in an Ableton live set or in whatever program you're using to make the music. And whatever you do with the music app, it should replicate it visually behind you on a projection. So how does that work for the performer? The performer would, when they're creating their live set, provide video material for all of the pre-recorded samples that they want to project on the screen. And then they also set up a webcam or some kind of capture device live that's looking at them so that whenever they're recording loops live, the webcam will record the video for that loop, and whenever they play that loop back, the webcam video will be projected behind them. If that makes sense. You can imagine with this video here that all of the videos that you see of me would actually be recorded live on a webcam. So that we're creating this tapestry of, or we're creating this grid of visualizations or of clips that are all actually based on the live event and that are proving to the audience that this stuff is not created, this stuff is not completely prepared beforehand. Like there is a real performance happening in front of them that's creating the sound that they're hearing. Okay, so I would like to give more detail to how this would work from the perspective of the performer, but right now I think that's about enough. The main point is that the performer shouldn't be doing anything extra to make these visuals work. If they're working through Ableton or they're using a looper like a Boss looper or a loop pedal system, I want to find a way to get the data out of their hardware or their software to be able to automatically create the video counterpart to their audio performance. I don't want them to have to do any extra work during the performance. They should focus on the performance. But okay, what I will detail now is how can this work from a developer's perspective? What's difficult about this project, and why do I kind of want to do it? So the way it works internally, how the system will work internally, is it's reading state from Ableton or reading state from whatever device you're looping on. I think I'm going to start with support for Ableton and then work my way outwards. It reads state from Ableton. And it can do this in a few different ways. One way it could do it is through intercepting MIDI messages. Let me show you this. So, Ableton push. So you've got devices like this. You've got the Ableton push. You've got also the Akai APC40. You've got cheaper versions like the 72 version, the APC Mini. And these, oh no. Let me just go images of the Ableton push here. So actually I prefer the way the Akai APC looks. Yeah, so let me show you this. Can I just get the image? Yes. Okay. So what you have on this Akai is basically a physical equivalent of the clip view or the session view that you have in Ableton. You have one button for every clip that you want to play or any clip that you want to record into. Then you have like the record enable buttons, and you have the scene launch buttons here. So you can basically control all of Ableton through this MIDI controller, which means that whenever you do anything in Ableton or whenever you do anything on this device, MIDI messages will be sent from that device to Ableton. And the way MIDI works on Mac at the very least is that those messages are global to the entire computer. Any program that's listening to MIDI will receive those messages. So you can run a program in the background that receives the same messages that Ableton does, and from those messages can figure out what you're doing in Ableton. Another thing that happens is Ableton is sending messages back to this APC to color the buttons, to show which slots or which clips are full with data and which ones aren't. And the information that it's giving back, we can use that. That's kind of an even better way to figure out what the state of Ableton is, because Ableton will be directly informing us about which clips are being played, when they're being played, and also the timing information. So there's lots of information running around on your computer that actually gives away what Ableton is doing. All we have to do is collect the right data and in an intelligent way reproduce the internal state of Ableton from that data. And once we have the state of Ableton and we know which clip should have which video, we can then figure out which video to put on the screen. So we read state from Ableton, and then when we decode the state, we figure out what's being played. Is a pre-recorded sample being played? Is a clip that's being recorded during the session being played? And based on that, we can determine whether we need to play back a video that's saved on disk, or whether we need to record from the webcam, or whether we need to play back a video that was recorded from the webcam. So you have the Ableton state, you figure out what that is, and then from that state, you figure out what you have to do, or you being the program, what the visualization tool has to do. And from that information, you can basically break it down into simple play, stop, record instructions. So you would have an instruction that you can tell the video player, like, play this video at this time for this length of time. And then you would have a stop instruction where it's like, stop playing this, even that you were looping it for a few minutes, now stop playing the video. Or record instruction, which is like, from this point in time, start recording the webcam because I want to use that material later. And then you'd have like an additional play instruction specifically for playing webcam recorded videos. So we've broken down, like we start with the Ableton data, we break it down into what clips are being played, what clips are being recorded. Then we break that further down into what does the video engine have to do? Which videos does it have to play? What time does it have to play them at? And if there's any recordings it needs to make, which ones are they? When do they have to happen? Right, so that is basically the external interface. Everything from then onwards will actually just be a generic video player with a few custom features of recording. So that's where we get to the main system, really. So the main system will receive these play, stop, record instructions, and based on that we'll handle all the necessary video processing to get that material on the screen. So in the case of a play instruction, it will find the associated video file on disk, it will open it up, it will start decoding it, and then as it decodes out frames, those frames will be placed on the screen at the right time, synchronized to whatever the instruction told it to be synchronized to. In the case of recording, it will have to open up some live video feed that can come from, again, a webcam or a video capture card, and it will start getting that data in, and it will have to encode it. It will have to encode it into a compressed format and either store that on disk or store that in RAM temporarily. And as it's encoded, as it's building up this file, at some point it will get a new instruction to play back. And so as it's building up that file, it will go into it and start decoding and playing it onto the screen. So that's going to be the most complicated system, because you've got files that don't have a fixed length. Like you might be recording something spontaneously and then having to play a bit back of it spontaneously. So that's going to be very complicated, but I'm going to see how that goes. That'll be very interesting to figure out, because we're essentially building a streaming video application where there isn't any start time or end time. It's all just video material and timestamps and like looped regions, and yeah, it's going to be a bit of chaos to structure that properly. But that's essentially it. That's what I want to do. I want to replicate whatever audio is happening in video. And I think the kind of video processing necessary to do this will be very informative for anyone who wants to do any kind of real-time video processing application. Right, okay. Next thing I want to explain, like, how do I want to implement this? So the implementation for this will be, there are a few ways you can implement this. So there are a few things that already exist, which I want to show you. Yeah, let's go over here. So VDMX is a very popular tool in it's a professional video DJ software, and it's got a pretty big price to it, but you know, not unusual for audio video performance software. And it's got a massive system that allows you to do all sorts of crazy things, and I imagine that I would be able to do my project in VDMX, which will have the benefit that it could plug right into any other visuals that you're doing. However, I don't want to do this necessarily because VDMX seems like a big system, and what I actually want to do is explore the more low-level concepts of video processing. And I want to see, like, okay, how can I do this from scratch or from like the bare essentials as opposed to using a big framework. Yeah, and so what I want to do, instead of using something like VDMX, I want to use I want to do it in C++. And so for C++, if you're doing any video processing project, there are multiple options for how you can build it in C++. So let me show you. There's one big one, which is Juice. So the Juice framework is a framework developed by the guys at Roly, who make these software and hardware instruments. And Juice is a graphical user interface audio processing framework, and it's cross-platform. It allows all sorts of crazy stuff to be done. So if you want to make a graphical user interface application that works on Mac, on iOS, on Windows, on Linux, Juice could be a very good place to start from, because they basically do everything for you. And I believe their framework and their library is very nice. I haven't used it myself. I was speaking with someone about my video project, and they have created a video engine for Juice. So if you're doing any work in Juice, you can also use a video engine there that called, let me find it. I have it written down somewhere. Okay, Foley's Finest video engine. So this Foley's Finest audio software company have created a video engine inside Juice that adds a few classes that allows you to process video files directly in Juice using the same API, and also render it and display it on the screen. And what he's trying to do is essentially make an entire video editor in the Juice framework that's open source. So I believe everything that I want to do would technically be possible in Juice, but again, I want to explore the more low-level, fundamental ways of doing video processing, and I think the layers of abstraction added by Juice don't interest me so much. Okay, so another big one, if you don't want to use Juice, but you do want to get off the ground working very quickly, is OpenCV. So OpenCV is I think a Google project, but it's basically open source framework for computer vision processing. So any kind of stuff like face detection, mapping, like probably a lot of the Instagram filters and Snapchat filters you see will be using something like OpenCV or similar. And OpenCV has everything you need to do stuff with video processing. And I think this would be a very interesting way to explore it, because OpenCV seems really cool. But again, I wanted to go a bit more low level for this project. So I've finally, to get to the core of what I'm doing, I'm going to be using FFmpeg, which is a open source encoder and decoder for video files to be able to access the video data that I want, and then OpenGL to render my video data on the screen. So super simple, just C++, OpenGL, FFmpeg, and there's this one thing that I need called GLFW, which allows you to create just an OpenGL surface cross-platform so that you can render stuff through OpenGL regardless of what operating system you're on. That's what I'm going to be doing. Again, not the best summary I could have given, but that's essentially it. Okay. Hope you're still with me. Let's look at the timeline. So first thing I want to do is getting pixel data on the screen. Then I want to start decoding some video frames, and then I want to render video frames on the screen. That's what we're going to be doing today. These streams will start out a bit like tutorials, and as I progress through this project, it will turn into me learning and me not necessarily teaching and just trying to figure out how to solve a problem. And that will be quite interesting as well. But first of all, to get up and running, I will be basically leading you through how to set up FFmpeg, how to set up OpenGL and GLFW, and how to start rendering stuff on the screen. So let's do that. Right, I'm going to start with an empty project here. I've got video app, a video app Git repository, and what I'm going to do is just go to my desktop and clone this. Okay. Okay, so there's nothing in it. It's just empty repository. So I want to start out by making a few directories. I want to have a source directory and I want to have a library directory. I'm going to bring this into Sublime and create a few basic files. So we want to readme, video app, C++. And I want to also create git ignore. I want to ignore any like Mac DS store files. I want to ignore a build directory, and that's it for now. Okay, so that's my basic structure. I have a library folder, source folder, and yeah, let's get to work. So how do you set up OpenGL and GLFW on a Mac to start developing applications that are cross-platform? So the first thing I do is I install GLFW as inside the library folder. So if I'm here, I've got my library in my source folder. I'm going to go into the library and I'm going to install, I'm going to say git submodule add. I'm going to install a, let's see, what's it called? I have it written down somewhere, probably references. GLFW. So I'm going to say git submodule add. Oh god. So submodule allows you to put a different repo as a child into your repo. So here we've got GLFW, and I'm going to install it inside lib as under the name GLFW. So then it starts cloning all of the data there. The nice thing is that if you want to update GLFW, you can just check out a new version of that repo inside your repository. So we've got that installed. If we look here, we've got GLFW. We've got GLFW. We've got all its sources, its include files, everything you need. You've got some CMake lists. Okay, so we've got GLFW. How do we actually make an application that can use this? Well, I'm going to be using something called CMake. And the way CMake works is you create these CMake lists.txt files throughout your project, and they're explaining to CMake how to build your project. So these are like, if a README is an explanation to a human, then a CMake list is an explanation to a build tool. And you're going to be explaining how all the different files in your project should be built together. So let me just, let's start writing that out. So first of all, dependencies. If you want to use CMake, you'll have to do like brew install CMake. And so you'd have to have Homebrew. Homebrew is just the most practical tool, in my opinion, for just installing these dependencies. CMake is, as I said, it's like a tool that actually, okay, so in the way build tools work, you would have a compiler like GCC or Clang that actually compile your application. And the line of code that compiles your application can be a really complicated line, and the way it all gets compiled together can be really complicated. So we create a step above that called with build instructions, where we write those instructions, and then those instructions call the compiler and do all of the difficult work. So, okay, CMake is already installed, that's fine. So how does a CMake file look? You would start with like a CMake minimum required version. So I'm going to just say 3.13. I don't know if I'm actually using that version. And I'm going to give this as a project video app. It's going to use C and it's going to use C++. I want to use C++ 14. Okay, so now let's just doing a really basic version. We can add an executable. We can say video app, and it will have a like source main.cpp file. So if we go into source here and I create a file main.cpp, okay, so then I would have let's just have a really basic hello world main. I wonder if that works. It's giving me some complaints. Redefinition of arg v argc. Okay, let's see if that works. So in our CMake list, we're building our main file into the video app. So our executable video app will just have one file that creates it. So then I'm going to go outside here. So I'm going to list, we've got our CMake list, a README, a library, and a source. I'm going to make a new directory build. And inside build, I'm going to say CMake whatever is in the parent directory. So if we're inside build, I want to CMake this project. So when I do that, it did some work and it created a make file here. And a make file you can call to build your project and it will execute it. So then I say make, and it says building target, linking executable, built. Oh God, that's not what I wanted to do. So now we can run our video app. It says hello world. Great. Not a video app at all. But that's a very basic CMake setup. You can CMake your project and then you can make it. Alternatively, CMake can create an Xcode project for you. So I'm going to remove my build file folder again and make a new one, start over. And I'm going to say CMake the parent folder, but don't make a make file, make an Xcode project for me. So it will read all these CMake files and output an Xcode project. So if I open up this build folder, I now have videoapp.xcode project. And when I open that up, I will have video app here in source files. I have a main.cpp. So I can then build it in Xcode, which is great because now I can use the Xcode debugger. There we go. Hello world. Program exited with code 0. So that's very cool. Let's link to GLFW. So the first thing I want to do is I want to add it as a subdirectory. I want to add GLFW there. So then what that means is it will go into library, it will go into GLFW, and it will find the CMake lists file of GLFW, and it will read all of that out and basically create a new thing for you to link with. Then all I want to do is, after I've added my main file to my executable, I want to also target link libraries. So my video app, I want to link GLFW, and yeah, that's probably it for now. I just want to link with GLFW. So let's try that. Okay, generated, all done. So now let's look in Xcode and see if it's working. So it's building GLFW, it links with it, it's all good. We're running the video app. Now let's write some code that we use where we use GLFW. So we can keep that, but I want to include GLFW free.h. Instead of printing stuff, I want to create a window. I want to initialize my GLFW, and if it didn't initialize, I'm gonna like printf couldn't init GLFW, and we just return -1 or return 1. Okay, I still need my standard lib. So let's see if that works. Can we initialize GLFW like that? Yes. So I want to create my window. Let's see, 640, 480. Hello world. Okay, if we don't have a window, if we couldn't open that window, then again I want to printf couldn't open window, and then just exit. So the problem is if we open a window and then we just exit out of main, the window will disappear immediately. So we actually have to stay open, which means we have to create a run loop. So first of all, I'm going to say the window that we just opened, that's the window that I want to be operating on right now in this thread. So I'm going to make the context current. And so then while, as long as the window should not close, we can just say see if we could just keep it open like that, just nothing. Maybe GLF wait events. So we initialize GLFW, we create a window, and then we stay in this while loop, waiting for events from the user, as long as the window should not close. So let's try that. Amazing. So we've got a window. There's nothing on it. Can we close it? Yeah. So we were able to exit out of that loop by pressing the X button, or probably by doing Command Q as well. Perfect. So that's a super basic GLFW setup. So in our CMake lists, all we've done is just linked our library GLFW and created our executable with a main file. That's it. Okay, let's render some stuff on the screen. So with GLFW, inside here, we can do our rendering. So we can use GL commands like GL clear, GL color. We want to clear GL depth buffer bit. And then I'm going to use a really old command like GL draw pixels. I want to draw 100 pixels by 100. It's going to be just GL draw pixels allows you to just get a buffer of pixel data and put it on the screen in like the most crude way. So we have to create a buffer first. So let me just do that outside of the while loop. I'm going to just create an unsigned char buffer data. And I'm just going to say, well, new unsigned char, it's going to be 100 by 100. And each pixel has 3 bytes, a red, green, and a blue byte. So I want to fill all of that with red, the color red. This is really crude, but it gives you an example for how you could just get data on the screen, because that's what we want to do. So there. Now, let's see. Data. Okay, so in this buffer, we've actually just got one buffer for all of the data. We don't just have like one buffer for each row of data, which means you'll have 100 pixels of the first row in bytes, and then 100 pixels for the second row, and then 100 pixels for the third. So the way you address all of that would have to be like, okay, if y is 0, if y is 2, then we have to go 200 rows down and then get whatever the x coordinate is. So we have to do y times 100, and for each pixel they're free, so that plus x times 3, and that, let me show that here. Okay. This is how I could fill a buffer with data. Let me see. So data at this point will be the row. Let's see, how do I explain this properly? So, if this is my image, then every pixel, let's see if I can do this properly. Okay. Every pixel that we have will have a red, a green, and a blue byte. So the way we would store this is RGB. You can imagine it like that. You'd have RGB, 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 RGB. And so this 5 by 5 image would be stored like this. So it would just be one whole row of data starting with X0, Y0, the red, the green, and the blue component. And then X1, Y0, the red, the green, and the blue component. Then X2, Y0, until you get to the end of the line, and then you start with Y1, X0, X1, X2, X3, and then row 2 and row 3. That's how the data is packed together. So if I want to create a 100 by 100 pixel image and fill it with all red pixels, then I have to, for each X and Y, I have to find the red, the green, and the blue byte and fill them with, well, the red one with 255 and the green and the blue with 0. So we end up with here, what we have here, Y, like we have the width of that one line, so that for row 1, we have to skip over 100 pixels, which means we have to skip over 300 bytes. For row 2, we have to skip over 200 pixels, which is 600 bytes. So we do whatever the width is times the amount of bytes per pixel. And then if the x coordinate is 2, we have to skip over 2 pixels, which is 6 bytes. So we have to times it by the size of each pixel. And then that will be the red component. And then one byte further will be the blue component, and one byte further again will be the green component. So we get red, green, blue. Right. So with this code, I've filled into this buffer all red pixels. And then with GL draw pixels, I could explain to OpenGL that I'm giving it a buffer where all the pixels are packed in RGB order, and that I want to print it. So I tell OpenGL, like, well, the width is 100, the height is 100. It's going to be RGB packed, and the type of each, like, let me just do GL draw pixels. Oh, it doesn't tell me. I was hoping it would give me the documentation for it. Yeah, so this is the documentation here. We say the width and the height of the pixels we want to draw, the format that the pixels are stored in, and the type of each byte or each component of the pixel, and then a pointer to our data. So that's what we're going to do here. We've got that the format is RGB packed. Each component of the pixel is an unsigned byte, and then we give our data like that. And then supposedly that might work. We'll see. So I'm getting some warnings. Yeah, it's deprecated. People don't really use this kind of OpenGL programming anymore. The tendency is to use shaders. I don't want to go into shaders too much right now because actually all I want to do is just put pixels on the screen. So I'm going to ignore those warnings and hopefully it will compile. So, okay, this is a common error. These symbols are undefined, but note that it happened in the linker, which means that when we're programming, we're aware that this function exists, but when the time comes to actually compile the program, we can't find the code for that function, and so it doesn't link properly. So in CMake, I have to link with GLFW, but I have to link with a few other things. So I'm going to link with extra libs, which is a variable I'm going to make. So I'm going to say if I'm running on Apple, I want to append to my list extra libs. I want to append, let's see, what do I need to add? Just framework OpenGL. Let me put in the Windows equivalent. You'll have to fact check me on this one. I'm not exactly sure if this is correct, but I believe to get those OpenGL functions to work, you have to link with LGLU32, LOpenGL32. Maybe it's just that one, but I'm not sure. Otherwise, let's assume it's Linux, and so then we want to just link with LGL, LGLU, LX11. I think that should work. For Windows here, apparently, you have to say CMake executable linker flags. I'm going to say standard equals to GNU99 static lib GCC static lib standard C++ M Windows. Apparently. So I will have to check this on Windows and make it fully cross-platform. But I believe those are the extra libs you need to link with to get OpenGL to work. So let's see if that works. So I have to run CMake again. And it successfully links. But I don't see any red pixels. And yeah, so what's going on? Why am I not seeing anything? We drew the pixels. Because we didn't swap the buffers. So when you're drawing with OpenGL in GLFW, you actually have one buffer that you draw your pixels onto. And when the time comes to render it, you have a back buffer and a front buffer. You have two buffers. One is shown to the user at any time, and the one on the back buffer is the one that you draw on. So you draw on your back buffer, and once it's full, you swap them around, and you show that to the user. And so then you start filling in your new back buffer. So you have to swap the buffers after you've done your rendering. Otherwise, whatever drawing you do will always be on the back buffer and never visible to the user. So I had to swap my buffers. So yeah, let's try that again. Okay, great. We've got a tiny little tiny rectangle of 100 by 100 pixels that are red. So there's pixel data there that I'm showing on the screen. Obviously, we want that pixel data to be video data and not just red pixels. But we're getting something on the screen, which I think is an important step towards putting anything on the screen. Because the code you see, even though it's doing something very simple, if you swap out the data there for any kind of other data, you will be getting any kind of other data on the screen. So this is like the simplest program you could have to render data on the screen. So actually, at that point, I'm gonna commit this. So I'm gonna add. Let me commit all of this. Add my gitignore file, my CMake list, my readme, my source file. Initial commit. Ugh. Great. I'm going to push that. Right, so there we go, video app in C++. In our library folder, you can see there's like this reference to GLFW. So it's actually not got any of the GLFW source code in my repository. It just has a little reference to GLFW repository saying what version of that repository we've checked out. So we've got our library, we've got our CMake list with all our important stuff. That's it. That's all we need. Yeah, cool. Okay. the next thing I want to do is I actually want to swap out GLF draw pixels, because draw pixels, as you can see, what happens here is when we draw these pixels, they show up in the bottom of the screen, and we can't actually just place them anywhere on the screen. It's going to be drawing our buffer in from the bottom corner into the frame buffer, into the back buffer, and that's not very flexible. So what I'd rather do is create a texture, which is OpenGL's term for like an image that you can place onto things and you can render in different ways. So I'm going to create a texture by getting my data, putting it into a texture inside OpenGL, and then you can instruct OpenGL to put that texture wherever you want. And you can also render it in 3D space. You can say this texture has to be floating at an angle, or has to be viewed in a certain way. And so it becomes much more flexible, and also every time you want to render the texture, you don't have to send OpenGL the data again. You just load it in once, and then it's stored on the GPU, and you can put the texture, you can render the texture multiple times. And there's all sorts of optimizations that go along with having that texture. So let's keep the raw data that we have, just this 100 by 100 block of red. Maybe I'll put some like a blue square in the middle by creating another loop here that starts from y25 and goes to y75 and x25 to x75. And instead of putting in those, I'm going to put in blue pixels like that. Let's see if that works. Oh geez. Yeah, so we've got our square with a blue square in the inside. Yeah, not very interesting. But yeah, so we've got that data. Now I want to load that into a texture so that every time we render, we can just render the texture. So in here, what I want to do is, let's see. So we're going to create a texture. So a texture will have an ID that we can refer to it as, which will be the handle. So I've got my texture handle variable, and then I'm going to tell OpenGL to generate one texture and give me back the name of that texture in the handle like that. And then we want to say, because the way OpenGL works is as a state machine. You place OpenGL into a certain state, and then you place it into a certain state, and then you can carry out specific operations on OpenGL. So when we say GL bind texture, our texture handle, I'm saying this texture ID that I have, I want to make some changes to this texture or use this texture right now. So from now on, refer to it as the 2D texture, the GL texture 2D, because that's the one that I want to operate on. And so, like at the end of that, once we've finished operating on that texture, we can then say GL, let's see. Yeah, no, we can then bind it to nothing. We can say GL bind texture 2D to 0, to null. So that we're now focusing on a different texture, on no texture. So that's the GL bind texture is like the next operations that we're going to do on texture 2D will be on the texture I just generated. So we bind a texture, then we want to basically say, what's the simplest way I can do this? The main thing we have to do is GL texture image 2D. We want to load in texture data into our GL texture 2D. There's a level argument that I don't care about. Then let me look up in OpenGL GL tech image 2D. Let me just show the documentation for this. Yeah, so first of all, the target texture that we want to work on, texture 2D that we've loaded in. The level is like how, like if you have one texture, you'd have level 0, which is like the highest quality version of that texture. And different levels will have different scales of your texture, so that based on where you're rendering it to, OpenGL can pick the most optimal version of your texture. So we're just going to say this is level 0. We don't care about different levels at the moment. Level 0 here. Level specifies the level of detail number. Level 0 is the base image level. Level N is the nth mipmap reduction image. So mipmap reduction images, we're just getting smaller and smaller versions of the texture, I believe. So yeah, we don't care about that. Then we have internal format, which is how should OpenGL store this texture internally. And I'm going to say RGB, just red, green, blue components. That should be fine. And then it wants the width and the height. Yeah, the width and the height of the texture. So it's going to be 100 by 100. What's the next thing? The border. We have no border. We have nothing outside of that 100 by 100 range. And then the format of the data that we're going to put in. The format and the type, that's the same as draw pixels. So it'll be GL RGB, GL unsigned byte, and then our data. So that's what we need to do to load in our data into our texture 2D. Now, I might be missing a few important things here to load that in, but we'll add that in later. Hopefully that should work to create our texture. Now, how do we render that? So I'm going to get rid of our draw pixels. I'm going to keep the clear function and the swap buffers function. But now to render it, we have to actually deal with the way OpenGL deals with coordinates and how it places stuff on the screen. So I want to do something that they call an orthographic projection. I don't want to do any 3D projection. I want to project it like on a flat surface, looking straight at it. And so I have to set that up. I want to make it so that when I refer to coordinates with OpenGL, like 0 or 100 or 200, I'm actually referring to the 0 or 100 or 200 pixels visible on the screen. When you're doing a 3D game, you don't want to think of it in terms of the X and Y pixels on the 2D surface. You want to think of it in terms of the 3D pixels, the 3D coordinates. But for my purposes, I don't want to do that. So I'm going to use an orthographic projection. So first I want to know the width and the height of our window. And I can use GLFW can tell us exactly the width and the height. I'm going to say get frame buffer size of our window and put it in these two variables. Next up, I want to go over to, oh God, I don't know why I did that. I want to say GL matrix mode, GL projection. I want to switch to, like there are two matrices in OpenGL, I think, or maybe more, but two important ones, the projection and the model view. So the coordinate system that describes how stuff is projected, then the matrices and the transformations regarding that is stored in the GL projection matrix. And then there's another matrix for the model view, the way the points inside the world get transformed. And that's in the model view. So the projection matrix describes how things should be projected, and the model view matrix describes how points should be transformed within the space. So if you want to change the camera, the way stuff looks, you want to change the projection matrix. If you want to place stuff after setting up the camera, if you want to then place things in the world, you have to use the model view. So let me switch over to have the model view below that. So here, set up orthographic projection. And here, after setting it back to model view, we can do render whatever you want. So inside GL projection, I'm going to load identity. I'm going to reset the matrix to an identity matrix. And then I'm going to use GL ortho to just fill that matrix with an orthographic projection. So if you look at GL ortho, yeah, okay. So it explains that in the world coordinates, if I give a value 0, it will go all the way to the left of the window. If I give a value of whatever right is, then it should be all the way on the right side. If I give a value of 0 in the y-axis, it should go all the way to the bottom. If I give a value of top in the y-axis, it will go all the way to the top of the window. And so if I set those values to be exactly 0 window width, 0 window height, then our world coordinates will be the same as the final window coordinates. Like if you put 20, 20 as your coordinates, then it will become the 20th pixel from the left and the 20th pixel from the bottom. So this is our way of basically saying to have a one-to-one mapping with the screen. No 3D projection, nothing strange happening from OpenGL, because we don't need it right now. The last is near and far. That's how to deal with the Z axis of if you have stuff in 3D. We don't care about that right now, but the basic values are usually just -1, 1. That's an orthographic projection. Once we have that, now we can render our texture. First things first, we have to bind with it. We have to enable our texture 2D, which says that whatever things we're going to draw, if we're going to draw a triangle or we're going to draw a quad or we're going to draw some kind of shape in OpenGL, we want to draw it with the texture. We want to use the texture as our paintbrush. So we want to do GL texture 2D. We want to bind specifically our texture handle there as our texture. And then we're going to begin drawing some quads. How do you do the quads? Well, first I say the texture coordinates 0, 0, the left bottommost corner of the texture should go to the vertex coordinate in the world of 0, 0. And then the texture coordinate 2D of 1, 0 should go to the world of 100, 0. The texture coordinate, and textures are basically 0 to 1. They're like squares. Like the coordinates for them are like that. Let's see, do we do 1, 1 should go to the vertex coordinate 100, 100. And text coordinate 2D 0, 1 should go to the vertex coordinate 0, 100. And that's wrong. And then we're going to say GL end. And after that, we're going to disable our texture 2D again. And that should render it. All these warnings is because I'm using old-fashioned OpenGL. I'm going to disable those. And so I'm going to go back into CMake and I'm going to here go add definitions, GL, silence, deprecation, because I don't care. If you want to learn to use proper shader language OpenGL, you will have to find that somewhere else, because I'm not interested in doing in building stuff with shaders right now. There's no benefit to me. I just want to get basic graphics on the screen so that I can do video processing. Right, let's try that. Succeeded, great, but it's a white image. Why is it white? What have I done wrong? Okay, I must give more parameters here for loading the texture. So I have to tell the way the pixels are stored. The GL unpack alignment should be 1. Perhaps that's the issue. I don't need to use CMake again. Okay, that's not the issue. I've written down some other things that I might need, so I'm going to write all of those back over. The texture parameters, parameter I, texture 2D, texture wrap S. I don't think these are what's causing the problem, but it doesn't hurt to put in all of the things you need to do. GL tech env environment and envelope environment. I don't know what this is. The part of programming that I don't enjoy, where you just have to copy specific things just to be able to then do the programming you actually want to do. You have to set up the environment in a very specific way, and you don't really know what some of the stuff means. And it's still white. Why is it white? We're giving it RGB, unsigned byte data. Let's see. GL quads, text handle. Why would it be RG? Why would it be white? It's as if... Is it like drawing to a depth buffer? Why does it have no content? Okay, that's not going to help me. Okay, let's see. We generate our textures. Tag width, tag height. Okay, that's very annoying. I don't know why I'm not getting any colors. Let's see if we can just move the coordinates around, first of all. So if we like offset it all by 200, and make it all twice as large. Okay, so we've still got our... Why is it white? Why am I not getting my reds and my blues? Unpack alignment 1. That's so strange. So the way it's reading my data is incorrect, but I don't know why. I don't know what is incorrect about it. Unpack alignment 1. Interesting. Let me see. I got another bit of code somewhere where I successfully did it. Let me check if I can find that. Stream notes. Color buffer bit, texture 2D. I'm doing exactly the same thing. What are the difference? What's the difference? Unpack alignment. Yeah. Is the data different? No, the data is not different. Oh, that's a much nicer way of doing it. Oh, yeah. Generate my texture. I don't know what's different. I don't know what's wrong. Gonna make the context current. When I'm generating my texture, I have to have the right context. Otherwise, the texture is not gonna be in the same place. Wow, that's stupid. There you go. So we've got our texture, we've got our data being represented or rendered in a certain place on the screen in OpenGL. Okay, now the next step, which is the interesting step, is to get FFmpeg running to, instead of having some fake data, have video data rendered to the screen. I'm going to take a short break and then come back in like 5 minutes and then start doing all of the work to get FFmpeg to run. Cool. Let's see about this. All right. Let's get back to this. Okay. Right. I'm cutting up this stream into multiple videos so that they can all serve as individual tutorials that people can watch. So if you are joining this as a video happening, if you're watching this as a separate video, what you've missed is that in the previous video I set up OpenGL and GLFW in a CMake project to be able to render some pixel data on the screen. So I'll show you what that looks like. It looks like this. We open up a window with Hello World as the title, and we've got this 100 by 100 pixel texture with our pixel data. So what I did is I gave OpenGL, don't save that. So it might look like it doesn't make any. It's a bit chaotic right now, but in general, up here, we have the essential part, which is I'm allocating a buffer of 100 by 100 by 3 bytes. So we have 100 pixels wide, 100 pixels high, and each pixel has 3 bytes. And then with this code here, I'm filling in every pixel the red, the green, and the blue component to have all red and no green, no blue. And then here, in a different range, Y ranging from 25 to 75 and X ranging from 25 to 75, I'm filling in only blue pixels. So what we get in this data buffer is an image with like everything red and then the center being this blue square. And then the code that I've made earlier is that I load that into OpenGL as a texture. So then we have our texture handle that we can then print to the screen whenever we want. So then I bind that texture and I draw it at these coordinates. So that's what we've got in the project. What I want to do in this one is start decoding a video file and get out the first frame of the video file and try and get that on the screen. So that will involve initially setting up initially setting up FFmpeg to start working with that library to start getting information about our video file. So I'm gonna quickly commit this. Commit all my changes. Git commit everything with the message pixel data rendered through texture. Okay, so how do we set up OpenGL? It's again, first, whatever operating system you're on, you have to install, not OpenGL. How do we set up FFmpeg? You have to install FFmpeg onto your system. And so the way I do that is just with brew install FFmpeg. And that will download FFmpeg, but it will also download all of the dependencies for FFmpeg. And FFmpeg is actually broken down into externally you can use it as this command line tool to convert audio and video files, but internally it has a whole collection of libraries that together form the FFmpeg functionality. Namely, there's AV codec, like internally it's called libav. So yeah, libav here. This is the library that underpins all of the functionality of FFmpeg. And it consists of AV codec, which is a library filled with different encoders and decoders for video files. It has AV format, which contains all the code for taking video data outside of containers, outside of the format. So if we look at a video file over here, so I have, let me open this up. So I have my demo song. If I get information about this demo song, it is an MP4 file. And so MP4 is the container or the format. And inside that MP4 file, there are different streams placed inside the file. There's audio data, and there's video data. Namely, what this more information is giving me is that there's stereo audio channels. So there's a stereo track of audio with the codec AAC, which is like Apple's audio format. And then we have H.264, which is the codec for the video data, which is 1920 by 1080. So inside a format, an MP4 container, you'll have multiple bits of multiple streams or packets or data. And inside there, you can also have like subtitle information. You can have metadata of like where it was made, who made it, the last time it was edited, what software it was rendered with or exported with. Lots of stuff can be put inside that file. You can also have multiple video files at multiple resolutions. You can do all sorts of weird like the stuff inside the way video file data is placed inside a file is quite complicated, and libav format is responsible for that. Next, you also have like libav filter, AV device, AV util, and so there are a whole collection of libraries that are used inside FFmpeg to make it do all those things. We're mostly going to be focusing on using AV codec, AV format, and AV util, which provides a few utility functions to make things easier. But first things first, we've installed it through Brew. How do we start using it in our project? Well, another thing I want to install, which will make this all easier is package config. So yeah, it's already installed on my computer, but that's what you need to do. Brew install package config. When you install FFmpeg globally on your computer, it will put the different library files, the files that your project has to link with and connect with to be able to run, it will store them in different locations. And package config is a tool that helps you locate where all those libraries are and gives CMake the information it needs to know where FFmpeg is and how to fit it into your application. So we're going to be using package config to create our library to link with FFmpeg. How I like to do this is every library I use in my project, I have a folder for it. So inside lib, I've got GLFW, which we're using for the rendering of graphics. I'm going to make a new folder called FFmpeg. And instead of any of the code being inside there, I'm just going to put one CMake lists file in there. And all the code, all the CMake information that I need to link and connect with FFmpeg, I'm going to put that in this one file. And then from our main CMake file, all I have to do is say add subdirectory lib FFmpeg or lib ff capitalized mpeg. And then when it comes to linking the libraries, GLFW extra libs, and I link with FFmpeg like that. I want to make it super simple so that like we hide all of the complications of linking with FFmpeg. So how do we link with FFmpeg? In the beginning of this file, again, I want to say the minimum required version of CMake, so that CMake knows that I'm like what version of itself is needed to understand this file. And I'm going to start a new project called FFmpeg. And inside here, I'm going to find the package config. And it's required. I need to use package config. By saying this, from here on forward, we can use package config functions inside CMake to help us find FFmpeg. It's weird. We have to find package config to then find FFmpeg, but it works. So we're going to use a function here called package check modules. And I'm going to say I want to look required imported target libav codec. So that's the name of the library, libav codec. I want to find this on my system, and it's required. I need it, and it's going to be an imported target. And internally in CMake, I want to refer to it as capitalized AV codec for now. I want to do the same thing for AV format, which on my system should be called AV format. And I want to do the same thing again for AV filter, AV device. I just want to link with everything, even though I might not use all of them right now. Lib AV device. What else do I need? AV util. Now, it might be that you don't need all of these libraries and then you don't need to link against them. But my assumption is that if you're going to have AV codec on your computer, that's because you installed all of FFmpeg, which means you would have all of these libraries. So it's not really, I wouldn't expect to see a situation where people don't have all of the libraries installed. But if you're preparing your executable in a specific way and you want it to be as small as possible, then only use the libraries that you need. But I'm just going to use all of it. So I also want these two special libraries called SW resample and SW scale. Actually, I don't need SW resample, but again, I'm going to link all of them just for brevity. Okay, so we've got package config to search and find information about all of those files, and to make sure that it has to find all of those, not files, all of those libraries. And now I'm going to say a library. I'm going to create a library in CMake. I'm going to say my library is called FFmpeg, and it's an interface. It's not an actual library, but I want people in other CMake list files to be able to treat it as if it's just a library that you can link. So it's going to be an interface that's imported, and I want to say, okay, within that library, there will be certain header files that I need to include. And so then I'm going to go through AV codec include dirs, all of the include dirs for AV codec, for AV format, for AV filter, for AV device, SW resample, and then SW sample, SW scale. So if package config finds these libraries, it will create variables inside CMake like AV codec include dirs, which will have all of the directories that need to be included by someone who wants to use that library. So we want to attach that to our new library FFmpeg so that everything that's needed to run FFmpeg will be prepared for us. So we need that, and then we need to set our link options for FFmpeg to link with all of the libraries. So AV codec LD flags, AV format LD flags. There must be a faster way to do this. All right, like this. LD flags. Okay. That's our FFmpeg library. Let's see if that works. So we add that as a subdirectory, which opens our CMake lists file, and then we link it with our video app. I think that should work. Let's see. Okay, so there's an error here, but before we look at the error, so it found package config, good, and then package config was trying to find all these modules, and it found libav codec with a certain version, libav format with a certain version. The only one it didn't find was rescale. That's wrong. It's libsw scale, not rescale. Just like that, SW scale. So that was just a typo. There we go. So configuration done, build files, we built it all. So now inside here, can we compile this? Yeah, cool. So let's start writing something with FFmpeg. We've now got an executable that's linking with FFmpeg, so it should be able to call some functions with FFmpeg and open a video file. I'm going to commit this again. Linked with FFmpeg. So this repository is available in the description. You can clone this and use this yourself. You can copy out files. There's no license. You can do whatever you want with it. Yeah, so that's the way I got FFmpeg to run and link. It took me ages to figure this one out, but that's the simplest way I could do it. Package config to find the libraries. Make sure that all the libraries can be included properly, and then all the libraries can be linked properly. And I haven't tested this cross-platform, so I need to see, but I believe that should work. That's a generic solution. Okay, I want to start making I want to start making a function, and I want to call it load frame. So I'm going to say bool load frame, and we're going to give it a file name, and it should give us back an integer for the width, integer for the height, and unsigned char data for the image data. That's what I want to do. And it returns a bool false when it fails. So that's the function I want to create. I'm going to create a new file for that called loadframe.cpp. And it will have that, we'll implement it here. For now, I'm just going to say return false. We just can't do it. In here, after we've created our window, instead of having just creating this data, I'm going to say int frame width, frame height, unsigned char frame data, unsigned char pointer frame data. I'm going to run load frame. I'm going to say users bmj desktop demo song. I think that's it, right? Demo song.mp4. That's what I want to open. And I want to get the frame width, frame height, and the frame data. If that fails, then I'm just going to return 1. I'm going to exit. Printf couldn't load video frame. And so then all of this code, I'm going to change it a bit. So I'm going to change it to the texture width and height will be the frame width and the frame height. And the data there will be the frame data. So the frame that we're loading will then be loaded into a texture, and then we can draw it on the screen. Here we've got to use frame width, frame height. I'm going to remove the... So, yeah, pretty basic right now. So in our CMake file, we now have to say that our program, our video app, doesn't just have a main, it also has that load frame.cpp. So it's going to be 2 files. Once this gets bigger, it's nicer actually to say list, append, sources, and then you have like source main.cpp, source load frame.cpp. And then for the app, for the video app, I can say it will have all these sources. So you can just list out all your source files there. Okay, so let's remake that and run this. Succeeded. Couldn't load video frame. Good, that's what we wanted because we're returning false. Now in here we could just, to confirm that it's working, we can say create a new, set the width to 100, set the height to 100, and we'll just allocate new data. And then I'll have a pointer, which will be data, start at data 0. And then I'm just going to do int x is 0, x until less than 100, plus x, y is 0, y is less than 100. I'm just going to say pointer plus plus equals to, no. I'm going to fill it with just red colors again. But this time written in a different way, like a really short way. Then I'm going to say true. Let's see if that works. So now our load frame will actually just give us a red block. Perfect. So we've got our red block there. So instead of just loading in a red block, I want to load in an actual video file. So let's try that. We'll turn this back into false. And we've got to start including some of FFmpeg. FFmpeg is all in C. It's not C++. So when including it, I want to tell the compiler, like, the code in here is not going to be C++. Don't think it is. Interpret it as just C code. So I'm going to include the AV codec. I'm going to also include AV format. I'm going to also include, you know what, that's enough for now. I also want to have int types, just to be able to say like u8, uint 8t instead of unsigned char. Like uint 8t is clearer that it's an unsigned integer of 8 bits. Like I prefer that. So int types gives you all of those type names. Okay, how do we open a file? First things first, we want to, the function we want to use is AV format open input. And let me see if AV format open input. Okay, that's the file. So it takes a format context, a URL, an input format, AV dictionary. So we don't want to give it any options. We don't know the input format. We want it to figure that out itself. So those will be null. The URL will just be that file name. And then for the format context, we need to give it a context that it can put the data in. So we start at the top by creating a format context, allocate a context, and we can also check, like, if it didn't allocate a format context, there's something that went wrong. So we can send like printf couldn't create AV format context, and we return false. But if we could create it, we want to give it to our open function here, like that. So we want it to open our input and put the information about that open file into our AV format context. AV format open input will return a boolean or an integer based on if it succeeded or not. So we want to just check that the result we got is 0. Anything other than 0 would be an error message. So I'm going to say couldn't open video file in the case that it's not a non-zero return. Yeah, like in this situation, you might want to like free up the context, because we allocated this context. We might want to free it afterwards. But like if we can't open the file right now, that's an error that will crash the program. We're going to stop the program anyway. So I'm not going to think too much about how to properly deallocate the resources as of yet. Okay, what I want to do is stop there and run that and see what happens. Couldn't load video frame. Why do we get that message? Because we do all of this and we return false. And then in the main function, we say couldn't load video frame. So that means that we actually could load the video file. We did open it. So I'm going to go into Xcode, go to our load frame function, and put a breakpoint at the end there and run it. Okay, so here's the cool thing. We can then look at what AV format looks like. It's a shame that I can't zoom in on this. It's a bit small for you guys to read. But what we have is we've opened it up, and we have a few things that we can look at. We have, let me see. If we go to I format, input format, the name, so it's like an MOV, MP4, M4A. The long name, it's a QuickTime movie. Extension, so it can have an MOV, MP4, M4A, FreeGP extension. But we know that it's a QuickTime MOV file, which is cool. We can also look at duration there. Duration is 2 million. Let me just copy this. That is probably in milliseconds. So if I divide it by 1,000, how is it that long? Is this duration in samples? Bitrate 0. Start time. It looks like these haven't been set yet, honestly. So we're not getting much information just from opening the format. We want to actually find some video data inside the format. So we've opened our file. We now want to go looking inside the file for streams, for video streams and audio streams. So the way you can do that is essentially just iterate over all the streams. So inside AV format context, we have a number of streams, and we can access them through AV format context streams I. So let me just say auto stream there, get the stream out, and here I'm just gonna put just a dummy bit of code so that I can put a breakpoint there. So iterating over all the streams. So we stopped here and we have a stream. Stream index is 0. We have a codec. So we can look at the codec. It's an AV media type video. So it's a video. The codec ID is H264. So the first stream in our AV format context is the video stream. I see a width 1920, a height 1080, a pixel format. There's lots of data here that I'm not going to use, but essentially that first stream that we found is the stream that we want to get the video data out of. So how do we turn that into code? We want to say, basically at the end, one of these streams will be the video stream. So I'm going to say video stream index is -1, and I'm going to try and find my video stream, and if it's found, it's like pseudocode, then I'm going to set my video stream index to that I to remember it. I'm going to break out. So if after that loop my video stream index is still -1, we have never found it. So then I'm going to say couldn't find valid video stream inside file, and we're going to return false. Okay, so how do we check this? So we have our stream. Let me go further through my notes. So we're going to get codec parameters. AV codec parameters. AV format context streams I. Codec par. And then for that codec, we want to find a decoder. AV codec find decoder. So you can see now that after just unpacking the format with libav format, now we're using libav codec to unpack the codec within the file. And so given the codec params codec ID, I want to find if we have a decoder, if we have the code necessary, like we have a program that's able to decode that file. So if we have it, I want to say, like, well, if we don't have it, if we don't have an AV codec, then that's an issue. We probably want to continue looking through all of the streams. Maybe we can find a codec that we can decode. But really, that's not a good sign. You might even want to just break from that. But I'll leave it like that. If the AV codec that we found, if the codec type is AV media type video, we found a stream that's a video stream. You could find the same thing, like one of these streams might be an audio stream, and it would be AV media type audio. And then you can extract stuff like the channels and the sample rate. and determine what kind of audio file you're dealing with or audio stream you're dealing with. But if we just found the video, we found it, okay, that's basically this code here. We've got our video stream index I, and then we want to break out. But we want to keep both of those, so I'm going to put those outside. AV codec. So that we keep them like that. What's the error? Codec type? What's it supposed to be? Oh, sorry, it's AV codec params. AV codec params is a video. That's how we can find the video stream. So, okay, let's run that again and end at the end there. Okay, so we've blocked. Our video stream index is 0. So we know that the first stream inside the MP4 file is the video stream that we want. So that code works properly. You could also look for, like, I don't want to look for audio, but you can also look for the audio stream index. You can set that to -1, and then you can say, like, if AV codec params codec type is AV media type audio, then we found our audio stream. But then in that case, you wouldn't want to break here. You want to be able to find them both before breaking through the loop, breaking out of the loop. But so I'm going to keep it just as video right now. We haven't used that. Yeah, we don't need that. So yeah, no AV codec, we continue. If we find a codec that's a video, we find a stream that's a video, then we found our stream. Perfect. So I'm gonna start commenting stuff out, commenting some of this stuff. So open the file using libav format. Find the first valid video stream inside the file. Okay, that's it. Now we have to start doing the real brunt work of taking video data out, getting video data out of getting the actual pixel data out of the video, which means using a decoder or a codec. So, right. This is where it's gonna start getting kind of tough. So all of these things, you have to do every single thing right to get the video file out. And you can just copy and paste this from another project and use that, but if you're gonna really do some video streaming, you have to understand how all of these parts of FFmpeg work together, and you have to call them the right way. But yeah, let me first set up my codec context. So, okay, let's go into here. Set up a codec context for the decoder. So, when you have an AV codec, that basically means you know, or FFmpeg is telling you that it has a program that can decode your video. And what you need to do is, if you want to start decoding it, you have to allocate data, you have to allocate space where it can store its internal data structures for decoding. And that's the codec context. So I'm going to say codec context. I'm going to call that my AV codec CTX. AV codec alloc context free, given our codec pointer. Right, if that failed, if we failed to allocate a codec context, that's pretty bad. So we're going to just print out and say couldn't create AV codec context, and we return false. Right. What now? What now? What now? What now? We have to, the information that AV codec, that libav codec or libav format, the information that libav format got out of the file has to be placed into our codec context as its initial state. So we basically do AV codec parameters to context. So we have our AV codec context and our AV codec params, and we're going to load them in. And if that doesn't work for some reason, we're again going to fail. We're going to say couldn't initialize AV codec context. Okay, so if now that that's succeeded, we want to open the codec, the file, and we want to start reading from it. So AV codec open to AV codec context and AV codec, and what's the last option? I've written down that it's supposed to be null, but let me just confirm why. Oh, it's the options. Yeah, we don't have any special options right now. If that is a negative value, that means it didn't work. So I want to just again printf couldn't open codec. Return false. Okay. Oh wait. Okay, so at the bottom here, now that we've done all of that, I'm gonna properly let's see. I'm gonna just write the close input. Just have all the destructuring done. Free the context. AV codec free the codec context. Yeah, so that happens at the end. So we open the file, we find the video stream that we want, and then we open the codec for the video stream. And then lastly, we just properly clean up our routine at the end, freeing up the context that we allocated and closing the input file so that the file doesn't remain open. Right. Oh, okay. That's a lot of stuff. That's the main setup for using libav. Now we want to actually start extracting out data frames from the codec. And that will require knowing a bit about how video files are structured. So how do I explain that? Let me see. Okay, so a video file internally is broken up into different units. Ones are called packets and others are called frames. So a packet inside a video file, basically a video file has all sorts of packets in it, just one after the other, one packet after the other. And the packets come from different streams. So when you read in a packet from a video file, it might be the packet for the audio, it might be a packet for the video, it might be some kind of data packet or something else. When you're looking for the next frame in a video file, you're going to be looking for packets until one of them is a video packet, and then you're going to decode that packet to figure out if there's any frame data in there. And for one packet, there may be multiple frames stored inside it, I believe. But it may also be the case that for one packet, that there are multiple packets that are required to describe one frame. So I'm not exactly sure about the relation between this. Okay, so the AV packet stores compressed data, and AV frame, I believe, would store uncompressed data. Okay. Yeah, so AV frame is the decoded raw data. So we start by getting AV packets out of the file format, and then we put those packets into the codec, into the decoder, and the codec will then give us an AV frame, which will have the raw audio or video data. So let's try that. So first we want to start getting packets out of the data. So let's create a packet and an AV frame. An AV frame and an AV packet that we can use as variables. So we'll have an AV frame, AV packet. I want to allocate my frame. If we didn't manage to allocate, then we want to error, couldn't allocate AV frame. Like with these, I don't really understand why you would. I feel like the program should just crash when you can't allocate a frame or something like this. Like these seem like errors that are never really going to happen. So I don't know why I'm writing them all down. But this is like for every single one of these. Some of these would only fail if you're like out of memory. And I really don't know how often that actually happens, because your computer will just free up memory and put it, like, swap it out to the hard drive. Like you'd have to be in a really bad situation to ever get any of these errors to happen. And if you're in that situation, having an AV codec uninitialized is like the least of your problems. So like the whole rest of the program will never function anyway. So if I would write all of this, I would have just written like, if it was just, if I wanted to simplify it, I would not check for these errors. But for the sake of following the rules, doing what everyone else seems to be doing, I'm going to be checking for those errors. All right. We've got a frame, we've got a packet. So we want to use AV read frame, where we give our format context. Format context, again, is the first thing that we allocated. It's the information about the file that we've opened using a libav format. From that format context, we want to read in a packet. The naming here, I don't understand. Why would you say read frame and then it's actually a packet? Like it should have been AV read packet, right? Why is it read frame? Stupid. That's going to return us a number. If the number is greater than 0, that actually means that there is a packet that we've read. If it's going to be below 0 or 0, that it's either an error or like an end of file. There's no more packets left. So we're just going to look for a packet. I don't know. Maybe we don't need to do this in a while loop right now. Yeah, we do, because there's situations where the packet, the frame we received is not actually a video frame, so we have to go back through it and read a frame again and do the same code. So we want to put this in a while loop. We want to iterate around until we find our first video frame, and then we can break out. Okay, AV packet stream index. If the stream of this packet is not our video stream, then we're going to continue. We're going to continue looking for others, because this is, we don't care about this packet. We don't care about the audio or any other kind of data. We're waiting until we get a packet for the video stream. And so we'll get to line 71 if it's a packet for the video stream. And so then we want to send the packet to our decoder. And hopefully the decoder will then start processing it and eventually can give us a frame. So we do AV codec send packet. So we give our codec context, AV codec context, and our packet, AV packet. This will return a response. Let's see, int response. If the response is greater than 0, if the response is less than 0, there was an error. So we want to printf failed to send packet, failed to decode packet, and we can get an error string in that situation from, because the response will be the error. We can say AV error to string of the response, and we return false. So we're going to get a positive response, and like, how do we do this? So we're sending packets into the decoder, and what we want to do is receive a frame from the decoder. So we're sending the decoder packets. We want them to give us a frame. And so what we can do then is AV codec receive frame. We give it the codec context again, and we give it our frame that we want it to put it in. Again, this is going to give us a response. So we'll have another response here. And so if that response, like there's a few error responses that we might want to deal with, is like if the response is AV error E again, or the response is AV error end of file, then whatever packet we gave to the decoder, there's no frame inside it, or the frame has already been decoded or something. So we basically want to say, we want to break, we want to continue. We want to go and do another read frame and try and read another frame. So if the response is those two, we just want to continue. But if the response is actually anything else less than 0, then it's actually an error. We want to say failed to decode packet and give the AV error to string of the response. In all other situations, we're going to have either the number 0 or greater for our response. If it's, so in this situation, we've got a frame. We've received a frame somewhere. So let me just check this all. Yeah, we've received a frame. I'm going to say for now, put that if that's less than 0, and here int response. Yeah, that's why I wanted to use int response, so that we can print out the response. Maybe I'll put that outside there and say response. Send the packet, receive the frame. If AV error or AV end of file, we're going to continue. If the response is less than 0, we fail to decode. We want to actually return false. There's something wrong. At this point, we've got raw data decoded in our AV frame. So I want to just put again like a dummy statement so that I can put my breakpoint there. So breakpoint, let's run this, see how far we get. Ooh, couldn't initialize AV codec context. After I was explaining that this stuff would never happen, it happens. AV codec context. This might give a positive number as a response, so we have to check if it's less than 0, not if it's non-0. Okay, we got all the way over here. So we've read in a frame, we've sent the packet, we've received the packet. So if we look at what AV frame has got inside it, it's got some data inside here. Okay, so it's got a data array with 8 entries, and in the first one there's some data, in the second one there's some data, in the third one there's some data. It's telling us that there's a picture inside this. The width is 1920, the height is 1080. We've got a color space, we've got information about the format. So we've got, like, inside here, inside that data, we've got some uncompressed raw data now, which is great. Just to show you, like, let me just explain that. So inside a frame, we have data, and data 0, like the way they decode the pixel data is they have the different channels, like you have a red, a green, and a blue channel. They put those channels in separate buffers. So you have one channel for all the reds, one channel for all the green data, and one channel for all the blue data. In this case, it's not stored in RGB, it's stored in YUV, in YUV, which is like one luminance component for dark and bright, one like hue component for what the exact color is, if it's a red or if it's a blue or if it's a pink, and then a saturation component of how strongly saturated is the color in the pixel. And so it's broken up in a different way. It's not just components of red, green, and blue. But the luminance one, we can use that to get a grayscale image. So before doing any complicated processing, I'm just going to break out here. And before I break, I'm going to basically, when they give you a packet, it's reference counted. So what I want to do is packet unref the AV packet and say, I'm not, like, you gave me an AV packet here, I'm not using it anymore, so I'm going to unref it. Here, what I also want to do is AV frame free, and give my frame an AV packet free, and give my packet. So I'm going to free up all my resources. But before, I'm going to break out, and here I've got an AV frame, supposedly. So my AV frame, I want to get the data out of that and put it into a square so I can put it on the screen. So first I'm gonna allocate some data. So unsigned char pointer data is new unsigned char array with the width and the height of the frame. Width times AV frame height times 3 pixels for each. We're going to make RGB data. And then I'm going to basically just copy over. I'm going to have a Y. I don't care about the efficiency of this. An X that goes from X to whatever the width is. And a Y frame, whatever the height is. And then we're going to fill in our data here. So, is this a redefinition of data? Up here, I'm going to say width out, height out, data out. So the parameters there are not mixed with our code over here. So we're going to have our data. I'm going to say Y times AV frame width. Oh, let's see, AV frame width times free plus X times free. That's going to be our red component, our blue, our green. So now our data doesn't have any actual data. It's still a red block, but it will have the dimensions of our frame. So let's just return that real quick. We're going to say width out will be AV frame width. Height out will be AV frame height. And data out will be our data. So let's see if that works. I hope it does. Couldn't load video frame because I returned false. So I have to return true there. Okay, that's big. Oh, there we go, yeah. That's 16 by 9. So that's the video frame. We've loaded, well, it's not the video frame, it's just red. Let's get the actual data out. For the time being, I'm just going to extract the data from the luminance of the frame. So we're not going to get the color because we need to convert color space properly to actually get a color image on OpenGL. But I'm just going to get the black and white image. The way I can do that is the way the data is stored inside AV frame is, if you see again, so inside AV frame there's a data. Let me pause it here. Let me put a breakpoint there so we can see. Inside AV frame, we have these data components. We have data 0, data 1, data 2, which correspond to the luminance, the grayscale color component, the U, and then the V, like the color components there and the grayscale components. And in those arrays, all of the data is stored consecutively. You just have one byte after the other. And so at some point, you basically start in the top right corner of the video and you have all of the video pixels. And then at the end of that line of bytes, you start describing the pixels on the second line of the video, on the second horizontal, then the third, then the fourth. And so there's another variable we need to be able to turn this one buffer into an image, which is how many bytes are there per line. And that's described in line sizes. I hope you can see this, like it might be much too small. But inside line sizes, for each piece of data we get the line size. So it's telling us for that luminance data that the line size is 1920. That if you want to get the first pixel of the second line on that video file, you will have to look at byte number 1920. If you want to get the second pixel, it would be byte number 1921. So we can use that to extract out the data. So I'm going to say here in my code, let me switch back to this for a second. I'm going to say in my code that we want to get AV frame data 0, and we want to extract out whatever the Y value is times by AV frame line size 0 plus X. That's going to be the grayscale pixel data for X. And we're just going to put that in the R, the G, and the B to just get a grayscale image. And so let's have a look at that. Let's see if that runs. Okay, it does. It does. And so we're getting the data from the sample image, but it's upside down. So why is it upside down? I guess I could just flip it in OpenGL. I'll flip it in OpenGL. So in OpenGL, when I say ortho, I can say that when you refer to 0, you're actually referring to the window height. And when you refer to the window height, it's 0. Let's flip around our projection. Yeah, there we go. Black and white data. Okay, so that is the first frame of the video loaded in and rendered onto an OpenGL surface, but it's only the black and white data. So that's a good intro for now. I'm going to take another break, and then I'm going to go into using the FFmpeg library SW scale, which here, like, it's apparently, like, within FFmpeg, within the developers, they don't really like SW scale. But we're going to use the SW scale library that comes along with FFmpeg to do color conversion, and you can do scaling with it, but we're not going to scale the pixels. We're just going to do color conversion to turn a YUV video, a YUV pixel video, into an RGB frame. So yeah, that's what I'm going to do in the next video. I'm going to take a break, but yeah, I hope you're interested. Okay. Oh, wow. Okay. 2.5 hours live streaming. Um, Programming for 2.5 hours seems completely fine, but then programming and then explaining every step for 2.5 hours it's intense. It's taking a toll on me, like for sure. But anyway, okay, so this is actually all live streamed, and I'm breaking it up into individual tutorial videos for YouTube. If you're watching one of these tutorial videos, for context, in the previous video, I went through setting up FFmpeg to decode an individual frame, just from so basically how did I do that? So if I look at my load frame code, we start off by opening the file using AV format. Then we select our stream, like we unpack this file, and inside an MP4 file or an AVI or whatever the format is, there will be multiple streams. There will be an audio stream, there will be a video stream, there will be other metadata, there could be subtitle information. And I look only to find a stream that is a video stream. And once I have that, and once I know that I have a decoder for that, I set up my decoder to open up whatever data is coming in from AV format, and in AV codec, it's going to start decoding it. So we initialize that, and then we have this main loop where AV format will read a frame, we'll take a frame out of well, actually we'll read a packet. We'll read a packet of data outside of the video file, and provided that this packet is relating to the video stream, we pass it into our decoder. We give a packet to our decoder, and the decoder will give us back a decompressed raw video frame. And that frame, what I'm doing now, is I just unpack the luminance data of how bright or dark each pixel is, and I'm putting that into an RGB format by just putting the brightness as the R, the G, and the B, and as a result, I'm getting this. I'm getting one image on the screen, which is a black and white image, because we don't have color data. So what I want to do now is, instead of just copying out the luminance of our decompressed frame, is actually converting the frame correctly to red, green, and blue so we can see everything. And the way we can do that is with a library called swscale. It comes along with FFmpeg, and all I have to do is just include it, which will be maybe LIVESTREAM slash, what is the things that I have to include? swscale.h, like that. I think that's it. Let me just check by running it. Yeah, that's the right include file. So we include this, and so at this point here, we have a variable. We have an AV frame variable called AV frame, like that, and that stores the raw data that's been decompressed by our codec, and it will store it in YUV format. So what is YUV? Let me just rely on Wikipedia here. So YUV is a color encoding system typically used as part of color image pipeline. It encodes color image or video taking human perception into account. So yeah, so this is a great example here. So we have a color image, and YUV breaks that image up into 3 components. We have the grayscale image of just the brightness, and then we have two components which together can describe all of the colors in the image. And so it's not quite hue and saturation. U and V are would look like this. So the value of U on this scale and the value of V on this scale will describe every color that you can get. The reason why it's split up like this and not described as red, green, and blue is that humans notice difference in brightness much more than they notice difference in color. So what you can do is you can get away with storing less information about color and storing more about grayscale, and humans will never notice the difference. So you can kind of compress an image just by changing the format in which you store it. So in the case of this raw video data, if I pause it here at the point where we've decompressed it, if I inspect my AV frame, I will have, so you see here, AV frame is the frame we received. It contains a property data, which has spaces, which has 8 pointers pointing to data. Only 3 of them are filled. So the first 3 contain in order the grayscale pixel data in position 0, the Y pixel data or the U pixel data, and then the grayscale luminance pixel data Y, the color U data, and the color V data. Those are the 3 bits of those are the 3 pixel buffers that we get out. Interestingly, how many bytes are there for each horizontal line of the video? For the luminance, there's 1920 bytes for one horizontal line, which means that there's 1 byte for every pixel on that horizontal line, because this is a HD video, because it's 1920 wide. But for the U and the V color components, there are only 960 bytes to describe one line, which means that every byte of color is split up into 4 bits for one pixel and 4 bits for another, if that makes sense. Like 1920 bytes means you have 15,360 bits for the luminance data of a line. You divide that by the amount of pixels you have 8 bits per pixel. In the case of the luminance data, we put in 960, so you have 4 bits for the luminance. So actually we're storing half the amount of information for color than we are for luminance. And so that it's saving space by having it in a certain format. But for the presentation of that data, when we go into OpenGL, we want to store it in the format that suits the presentation, which is the display, and the display is RGB. We have a red, a green, and a blue LED, or we have a red and green and blue light emitting object on the screen. And by varying the intensity of those 3 lights, you will get whatever color you want. So we need to switch the format, and we can do this with SW scale. So my old routine of just copying over the grayscale data, I'm going to remove that. I'm not going to use that anymore. Instead, I'm going to create a SW scalar context, which is all the data that the scalar needs to be converting color spaces or converting sizes of the image. So I'm going to say SWS context, and we'll have our scalar context here, and we'll say we're going to get a context. We have to give it the width and the height of our video, so we have AV frame width, AV frame height. It's going to ask us for the pixel format, which our codec context knows. We can give it the pixel format. And what do we want to scale it to? What do we want to turn it into? Let me just show you get context. It has a few different things. It has source width, source height, source format, then destination width, destination height, destination format. So I don't want to change the scale of the image. So the destination width and height will be the exact same. But if you wanted to scale it down by a half, you could do that here. You could like divide the width there by 2, divide the height by 2, and you would get half the size image. So the software scaler can do that for you. The destination format. What do I want as my destination format? I want an AV pixel format RGB0, which means for every pixel that we have, I want 4 bytes. I want a red byte, a green byte, a blue byte, and then an alpha byte, which is just not used. But that's a very common internal representation for data, where you have 4 bytes for each pixel, where you have an alpha channel, where you can describe the transparency of the pixel. But here we're not going to use it, but we're going to get it to put it into that format. And okay, how do we want to do the scaling? So we have like the flags. We want to say, we just want to do SWS bilinear scaling or fast bilinear. Let's do that. That's even better. It doesn't really matter because we're not doing any actual scaling, so it doesn't have to interpolate pixels. It just has to change color values. So I'll stick with that. it should determine that the width and the height is the same and that it doesn't scale at all. But that comes in handy when you're actually scaling. And then we have a source filter, we have the destination filter, and we have parameters. We're going to set all of those to null. We don't care about any filters that we're applying. That's our context. That's our scaler is defined to do that. And so now we just need to give the scaler the information to scale our data. I'm going to change this a bit. I'm going to say put width and height on the same line like that, like this. So that's the input width, height, and format, output width, height, and format, and then these options on the third line. If we don't get a scalar context, then something went wrong. We're going to say couldn't initialize SW scalar, and we return false. In that situation, again, we should actually close all of those inputs, but you know, error handling, I'm going to do that later on in this project. Right. If you saw, it's really annoying that when I pause the debugger here, that it is so, that the text is so small. I wish I could do something about that. But inside AVFrame, you see we have this data array with pointers to all the data and a line size array giving the information of how many bytes are in each horizontal line of data for each of those buffers. So we're going to give that to our scaler. So we're going to say SWS scale. We're going to give it scalar context, and we give it the AV frame data, and we give it the AV frame line size, and we tell it to start from the horizontal 0 all the way up to the height of the image. But then as the destination, we have to give it another one of those data and line size vector or data and line size arrays. So we have to create one. Now, unlike the input where we have 3 different buffers, we actually want everything to go into one buffer where each pixel is packed in, where you have the red, the green, the blue, and a 0 for one pixel, followed by a red, green, blue, and a 0 for the next pixel, red, green, blue, 0, red, green, blue, 0, until the end of the horizontal, and then we have red, green, blue, 0 for the next one. So we want to pack it all into one buffer. So we're going to tell it that. We're going to say, we're going to create a uint8t destination buffer, which will have our data. Did I delete that? I deleted that. Okay, so I need to allocate my buffer. Unsigned data pointer data unsigned char pointer. I'll use uint8t data buffer. New uint8t of AV frame width times AV frame height times 4. We're going to have 4 bytes for every pixel because we're going to have an RGB alpha. And so in our destination, we'll have that as our first buffer, and all of the other ones will remain empty like that. And then we have to have one vector describing all the line sizes, which will be 4 again. And the line size of our data will be whatever the width is of our frame times 4, because we have 4 bytes for every pixel. So the amount of bytes in the horizontal of our video buffer will be 1920 times 4. Whatever the video width is times 4. And the line heights of all those other ones will just be 0. There's nothing in those buffers. So that's what we wanted to write the results into. So we're going to have destination, and we're going to have destination line sizes, and we'll see if that works. So yeah, let me just stop that and put a breakpoint after we do SWS scale and see what happens. Okay, so over here in our data, I see some stuff in there. So I see some data in there. That's really good. I want to see it on the screen. I don't want to just write it to disk or whatever. So let me first free the context. We don't need it anymore after we've scaled this one thing. The cool thing is if you're processing all of this video, you set up your scaler once, and then for every frame that you have, you do SW scale, and only at the end do you free the context. So when I start pipelining this where multiple frames will come in, then I need to manage these contexts properly so that FFmpeg gets set up once, and then we just run the functions for every new frame without changing any of the options. Yeah, so we've scaled that. I need to set, I want to set width out to the AV frame width. So for context again, if you're only watching this one video, I've got a load frame function that we're building here. And it takes a file name and it gives us back a width and a height and a data buffer. And so I just need to hand all of this back to whoever's reading so that they can put it into, so that they can read it. So I'm doing that. I'm going to free up all our resources and then return true that we succeeded in loading the frame. So let's run that, see if it works. Okay, that worked, but that's not a good frame. Okay, it's, I see. If I go to main here, we get our frame data back, and I'm telling OpenGL when loading in this frame data that it's in the format GLRGB, but it's actually in the format GLRGBA. So I'm telling it that the data that I'm giving it is RGBA, so it's actually 1 byte for the R, the G, the B, and then an A byte. It was misaligning it because of not knowing the format. There we go. Beautiful. So we have a properly decoded single frame from a video file going out of FFmpeg onto an OpenGL surface where we can project it, we can do whatever we want with it. If you think that seems like a lot of work to just get one frame, you might be right. But on the other hand, it seems like a lot of work to get one frame on the screen. But if you're gonna build any program that's animating stuff and that's actually streaming video, you'll need to control all of these individual steps. You'll need to do different things in all these steps. Like you see that we're like individually initializing the format context for opening up the file separate from the codec. But that's because you might actually want to treat the file in a different way, or only extract the audio, or have to extract both of them. So then you open your file, you get those two streams, and then you want to, when decoding packets, send them into your audio decoder and into your video decoder separately. So when it comes to creating an actual real-time video player, this would not be just one block of code. It will break up and it will actually touch lots of parts, lots of parts of your application. But for a single frame, this seems like a lot of work. But there we go. That's it would be cool to do some more work of like animating frames, but I'm pretty tired now. This has been a long stream. And I'm pretty happy that I can get one video frame on an OpenGL surface. Just let me change the file name and see if I can open a different file. Desktop, where are all my files stored? I have stream announcement announcement.mp4 on my desktop as well. Yeah, really cool. Okay, I'm gonna leave it there. As always, all of this code is available on GitHub. You'll find it in the description. You can clone this. You can copy out any of the. You can use any of the code that you want. Yeah, I'm going to check all of this in and I'm done. Color, how do I say this? Decoding video data out and rendering. Decoding first video frame and rendering to window. Push that. Okay. That's it for now. I'm going to leave it there. I hope I explained things in a way that is understandable, that you can get to work using FFmpeg now and you can start manipulating video files. Sometime next week, I will announce it. I will start animating videos on an OpenGL surface so that we can actually start seeing moving images, not just one image. But this is an important starting point where you see how an individual frame can be decoded. Once you know how to decode an individual frame, it's quite easy to then extend that to decoding multiple frames. The big challenge will then be when you're decoding all these frames, how do you synchronize them to the right frame rate? How do you understand when to render a frame? And so I will get into that in the next live stream. Thank you very much for watching. If you have, subscribe if you want to see more of these live streams, and I will see you in a week. Goodbye.